The James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The posts claim that the telescope captured the object changing its trajectory in an unnatural manner, meaning it must be some sort of extraterrestrial life.
3I Atlas has begun to shift its path in a way no one expected. The James Webb Space Telescope caught the first flicker, then another, until the pattern became impossible to ignore.
It's really a very anomalous object, perhaps natural, but we should allow for the possibility that it's something else.
This isn't a passing object anymore. It's drifting inward, off the track scientists mapped. And every mile closer to the sun, it gets more active. The deeper it goes, the less it looks like something we understand, and the more it looks like something we're not ready for. The signal Webb wasn't expecting. The James Webb Space Telescope had been observing an interstellar object cataloged as 3I Atlas. At first, it was nothing urgent, just part of a larger campaign to track unusual bodies crossing the solar system. The first infrared readings came back as expected. When the next batch came, the numbers had shifted. A small angular deviation, a nudge too small for most telescopes to notice. But Webb noticed. The deviation repeated again, then again. That was when scientists realized something fundamental had changed. The object was no longer following its original path. And it wasn't a random wobble. The motion was subtle but consistent. A slow drift, inward, not just toward the sun but toward a very specific part of the inner system. A zone of space that includes Earth's orbital region. No alarms were raised, but among deep space tracking stations, priority shifted. The conclusion was the same. The object's motion was bending. The shift is not yet cause for public alarm. It is, however, scientifically serious. 3I Atlas is not a local comet. It did not form near our sun. It came from another star system entirely, traveling for millions, perhaps billions of years through open space. These kinds of bodies don't show up often, and when they do, they don't stay long. So when one begins to change direction in real time, and that new path edges closer to Earth's orbital plane, space agencies notice, especially when the readings come from Webb, the most sensitive space telescope ever launched. Right now, 3I Atlas is still distant, but the closer it drifts toward the center of the system, the more the environment changes. Some scientists suggest this drift is driven by asymmetric outgassing, natural jets of sublimated gas pushing unevenly from the surface. Others wonder if deeper, layered processes are at play. Either way, it means one thing: the motion is no longer fully predictable, and that presents both risk and opportunity. The object is not on a collision course with Earth, but it is on a path that brings it through the orbital neighborhood, the wide three-dimensional region Earth moves through as it loops around the Sun. This matters because objects that pass through that region can be observed more closely than ever before. Their gas trails, spin dynamics, and surface shedding can be tracked in real time. But there's a deeper reason scientists are watching with such urgency. Every degree of drift now could mean a much larger divergence later, and with each new set of readings, it's becoming harder to say for certain where 3I Atlas will exit or what state it will be in by then. For the first time since it was discovered, the path is bending. The numbers confirm it. But is this just the beginning of the shift or a signal that something inside this object is starting to change in ways we don't yet understand? A body that woke up too early. The strangeness wasn't just in the motion. It was in the data itself. Webb's primary strength is infrared detection. It sees heat where the human eye sees nothing. And when it turned its attention to 3I Atlas, the first clear anomaly emerged: elevated carbon dioxide emissions. At this distance, that should not have happened. Typically, objects this far from the Sun are inert, frozen solid, barely active. Most comets don't show significant CO2 outgassing until they're within 2 to 3 AU of the Sun, roughly the distance of the asteroid belt between Mars and Jupiter. Their surfaces stay locked beneath crusts formed over millions of years in deep cold. But 3I Atlas was different. Its surface was already reacting to sunlight, and it was doing so early. The object was shedding carbon dioxide in measurable quantities, enough for Webb to isolate the chemical signature and monitor it night after night. What's more, the emissions weren't uniform. They came in uneven bursts, stronger on one side, weaker on the other. That pointed to active jets. Jets in this context are narrow streams of gas that erupt from surface cracks as ices beneath begin to sublimate. These aren't explosive geysers, they're steady, silent forces. But over long distances, even the smallest asymmetric jets can push an object off course. It's like trying to steer a canoe by dripping water from one side. The effect is slow, but real. This jet pattern suggested a structure that wasn't just melting, but possibly layered. Some researchers proposed a shell of fractured carbon crust overlaying deeper, colder material. If that's true, the current gas release is only the first phase. The deeper layers, still locked in extreme ice, haven't even begun to melt. More interesting still is what the carbon dioxide implies about the object's origin. CO2 doesn't freeze easily. For an object to retain this much of it, it must have formed in an incredibly cold environment. Some researchers have hypothesized that 3I Atlas may have originated near a dim red dwarf, the kind of low-energy star that fills the Milky Way but rarely gets attention. Stars like these can keep icy fragments stable for billions of years until a gravitational kick sends them flying toward interstellar space. But there was another surprise buried in Webb's data: the coma. This faint halo of vapor and dust that surrounds active comets is typically small this far out. Not with 3I Atlas. Its coma was expanding. Webb captured signs that the coma was being pushed outward more strongly in one direction. This matched the jet data and confirmed the object wasn't just reacting, it was reacting unevenly. These irregular patterns are exactly what make scientists nervous and excited. A stable, symmetrical object is easy to model. One that begins to heat on one side, spin unevenly, and emit irregular jets? That becomes a wild card. So far, the changes are slow, controlled. But every night Webb watches, the activity inches higher. These aren't dramatic signs, but in deep space, small changes have large consequences over time. The most important takeaway from Webb's early analysis is this: the object is already unstable, and the structure is changing. The behavior is accelerating, and the deeper it moves into sunlight, the more those changes will multiply. So now scientists are trying to predict what happens next. Because even though the outer layers are active, the deepest ices haven't even cracked yet. The shift. What caused the drift? The evidence pointed to uneven outgassing. Some areas on the object's surface were releasing gas with more intensity than others. Webb's thermal maps showed hotspots, not large but strong enough to produce localized thrust. These thrusts did not align with the object's center of mass, meaning each burst caused a tiny rotation or push. Individually, these effects were small, but over weeks of travel, they added up. It was not only the pressure of gas that mattered. The coma, the cloud of vapor around the object, had begun to expand in a lopsided way. On some nights, the tail bent slightly. On others, the coma bloomed wider toward the sun-facing side. These were subtle shifts, but consistent. Over time, they showed that one side of the object was becoming more reactive than the other. The twist in the path became clearer when orbital analysts added retrograde motion into the equation. 3I Atlas was not just approaching the inner system, it was doing so in the opposite direction of the planets. Retrograde motion increases kinetic energy in any interaction. It also amplifies solar pressure on specific regions of an object's surface. As a result, every asymmetric feature becomes more influential in how light and gas push the body. Scientists began to compare this with what happened to Borisov, the last confirmed interstellar comet. But Borisov moved quickly and stayed symmetrical. 3I Atlas was slower, more uneven, and more complex. The new orbital predictions placed the object near Earth's orbital zone in the coming months. It would not intersect Earth directly. Still, the path would move through the same region Earth occupies each year. This was not a threat. It was, however, a rare opportunity. The closer the pass, the better the data. Telescopes could study the object in higher detail. Radar teams could attempt shape mapping. Gas ratios could be captured in real time. But the deeper concern lay in the path itself. It was still changing. With each new outburst, the motion adjusted slightly. The orbit was not fixed. Scientists could not yet say when the drift would stabilize, or if it would. That uncertainty matters. 3I Atlas is now a moving system. Its own activity is reshaping its course. If deeper ices begin to vent, if larger jets open, the trajectory may bend again. It may grow more erratic or less. No one can say for sure. For now, the object is approaching Earth's region of space, not with urgency, not with danger, but with a kind of silent pressure, a pressure that continues to shift its line of motion with each passing day. And somewhere ahead, beneath its frozen crust, the layers that have not yet responded to heat are still waiting. If they crack, if they release gas, the path may twist again. No model is ready to predict that second turn. Rule breaker. From a distance 3. I-Atlas looks like a comet. It has a coma, it has gas jets, and it is shedding material as it approaches the Sun. But the comparison is only surface level. Deep down, this object does not follow the behavior of any local comet on record. Most comets in the solar system are well understood. They orbit the Sun on repeat cycles. Their surfaces respond to heat in predictable ways. Their outgassing follows established thermal models. But an interstellar object arrives without that history. It formed in a different place, under different radiation, with a different chemical profile. Scientists do not have a template for how it should behave. That's why 3I Atlas entering Earth's orbital corridor matters. It gives scientists a chance to see how a foreign body, untouched by our Sun until now, responds to the forces of our system. More importantly, it shows where our models may fail. In 2017, Oumuamua passed through our system so fast that most of its mysteries remain unsolved. Its lack of visible outgassing broke every expectation. Its path deviated slightly in a way that still sparks debate. With Borisov in 2019, there was more data, but it was still limited to a narrow window. 3I Atlas is different. It arrived early enough and is staying long enough to be tracked through its full transformation. The warning systems used to model local comets assume symmetry. They assume consistent surface behavior. They assume that motion is largely driven by solar gravity. 3I Atlas is proving those assumptions fragile. Its path has already shifted once due to natural outgassing. It may do so again. And if it does, our ability to model similar future objects may be tested in real time. For planetary defense teams, this is a high-value trial run because it behaves like a threat might. It enters quickly, acts unpredictably, and alters its own path through internal forces. These are the same features that would define an object we did not see coming. Even beyond the defense angle, there is a deeper scientific value. 3I Atlas offers a view into the material makeup of another star system. Each gas emission, each dust trail, each fracture reveals information about its origin. If it carries ices that only form at extreme cold, scientists can reverse engineer the environment it came from. That may tell them about the kind of star it orbited, the age of the system, or the chemistry of the protoplanetary disk it once belonged to. This object is not just a visitor, it is a test. It reveals how much we understand about objects we have never seen before and how much we still do not. And now that it is passing closer than expected, the stakes are higher. The instruments we designed to study local space are being used to decode something far older, colder, and more alien than we ever planned for. The heat zone. There is a boundary in the solar system that comets rarely cross without consequence. But for icy bodies like 3I Atlas, it changes everything. That boundary is heat. Right now, the object is crossing into a region where solar radiation increases sharply. This zone triggers a shift in behavior. Surface vents grow more violent. Jets become chaotic. Pressure builds inside. And for many objects, this is the point where the outer crust is no longer strong enough to hold together. 3I Atlas has not reached that moment yet. But it is close. Webb's data already shows rising infrared output. The gas ratios are no longer stable. Carbon dioxide, once dominant, is now fluctuating in strength. This could mean other ices are starting to react. Frozen methane, formaldehyde, even rare nitrogen compounds. If that's true, the object may be preparing to enter a more volatile phase of melting. Scientists have three main theories for what comes next. The first is structural breakup. If internal pressure exceeds what the crust can handle, the object could split apart. Many comets do. The result would be multiple fragments, each following its own path. These fragments would briefly expose layers never seen before, material from the object's untouched interior. It would be a moment of scientific gold, but one that passes quickly. Radar and optical systems would scramble to lock onto each new piece before they drift too far apart. The second possibility is a dust release event. Instead of breaking, the object could shed a thick cloud of fine grains. These grains, rich in volatile elements, would spread along the tail and give scientists a rare look at material that predates the solar system. Instruments on Earth and in orbit would use spectrometers to decode the cloud's chemistry in real time. The third scenario is the least dramatic but just as valuable. The object holds together. It survives the inner region and continues outward, shedding jets, venting gas, but keeping its structure intact. This outcome would give the longest observational window and allow direct study of how an interstellar object adapts to solar heat without disintegrating. Each outcome brings a different kind of science, but all of them require the same thing: constant observation. That is why every telescope with a line of sight to 3I Atlas is preparing. Ground teams are mapping the coma expansion night by night. Space-based sensors are tracking spectral shifts. Radar crews are running simulations for bounce mapping in case the object passes close enough. There is also growing attention on its spin. The jets may already be changing the rotation rate. An object that spins too fast can develop surface cracks. One that spins unevenly may begin to tumble. Either change would further alter the direction of the gas jets, which in turn would adjust the object's path again. This is how small inputs become large shifts. The deeper it moves into sunlight, the more fragile its orbit becomes. Right now, Webb's team believes the outer crust has reached a stable warm zone, but beneath that layer are colder cores. Once those are breached, the process accelerates. Ices do not melt slowly forever. They reach tipping points. When that happens, the release is not linear. It becomes sudden. If that phase begins, telescopes will see it almost instantly. The tail will grow rapidly. The gas content will spike. The object's drift could shift again. And once that happens, predictions become much harder to trust. For now, 3I Atlas remains on a safe track. But the heat zone is close, and every past interstellar object that approached this region changed. Some faded, some shattered. None returned the same. What makes this moment unique is that we are watching before the change begins. This is the first time an interstellar traveler has arrived early enough to witness the full arc, from quiet to reactive to transformed. And soon, it will meet the sunlight that no layer has ever felt before. What scientists fear? The current challenge is predictability. Each time 3I Atlas vents gas, even slightly, it shifts its own path. These changes are small, but they build. And for planetary defense teams, this creates a real-time case study. How well can we track an object that is actively changing its own motion? The concern is not impact, because 3I Atlas is not a threat to Earth. What matters is how well current orbital models can handle an object that breaks the rules. And so far, 3I Atlas is doing just that. It moves retrograde, spins unevenly, vents gas asymmetrically, and follows no known pattern. One concern among orbital analysts is that the models may not stabilize until 3I Atlas exits the inner solar system. That limits how far ahead predictions can go. Right now, analysts can trace the curve for the next few weeks with high accuracy. This has never happened with an object this size and speed. That makes every new piece of data valuable. So far, the object has passed no known hazard zones. It remains on track to move safely through the inner solar system and return to deep space. But its path is different now. It no longer resembles the clean arc it followed months ago. It has already shifted once. If the internal ice ruptures again, it may shift again. Instruments are being reconfigured to capture sudden changes in tail structure, venting patterns, and surface chemistry. Even radar teams are preparing shape scans in case the object drifts close enough for bounce imaging. Observations continue nightly as the object inches closer to perihelion. Every telescope capable of infrared tracking is now watching. When will the deepest ice layers breach? What chemicals will rise from inside, and what will they reveal about the long-dead star that formed this object?